All right, let's talk about one of the biggest ideas in all of physics, momentum. It's this invisible force, this rule that's running the show behind the scenes. I mean, we're talking everything from a simple game of pool all the way up to galaxies crashing into each other. It's the thing that decides what happens in pretty much any interaction you can think of. So think about this for a second. What on earth could a car crash, a rocket blasting off into space, and a game of pool possibly have in common? I mean, they seem like totally different things, right? One's chaos, one's pure power, and one's, well, just a game. But here's the kicker. The physics behind all of them is exactly the same. Yep, you heard that right. All of those things, and I mean so many more, they all come down to one single kind of beautiful idea in physics. And by the time we're done here, you're going to see exactly how it all clicks together. So let's dive in. Okay, so here's what we've got on deck. We'll kick things off with what is momentum. Then we'll look at impulse, which is all about the force of change. After that, we'll get into the big one, the conservation law. We'll see it in action with collisions, and then we'll wrap up with a little physics toolkit for you. All right, first things first. What even is momentum? Well, if you ask a physicist, they'll tell you it's the quantity of motion. But, a simpler way to think about it is just how much oomph something has when it's moving. It's that simple, really. Now, here's a super important point. It's not just about how fast you're going. See, momentum is what we call a vector, which is just a fancy way of saying it has two parts. The magnitude, how much stuff is in motion, and the direction. So if a car is heading north, its momentum is pointing north too. And trust me, that direction, it's going to be absolutely crucial later on. And this is the secret sauce, the formula that puts it all together. It looks so simple, right? Momentum, which we call P for some reason, is just the mass m times the velocity v. So you've got a heavier object or a faster object, bam, you've got more momentum. That's really all there is to it. Okay, let's put some numbers to this to make it, real. Let's say we have a car that's about 1,000 kilograms, and it's zipping along at 20 meters per second. All you do is multiply those two numbers. 1,000 times 20, that's 20,000. So its momentum is 20,000 kilogram meters per second. That number right there, that's its quantity of motion. All right, so we get it. Moving things have momentum. But how do you change it? How do you slow something down or speed it up? Well, that brings us to our next big idea, impulse. You can kind of think of impulse as the thing that actually causes a change in momentum. So what is impulse? It's just the force you apply to something multiplied by how long you apply it for. And here's the really cool part. That number you get, force times time, is the exact same thing as the change in momentum. They're not just related, they're literally two sides of the same coin. And this simple little formula has huge consequences. Think about it. If you need to create a certain change in momentum, let's say bringing a car to a complete stop, but you want to use less force to do it, what do you have to do? The formula tells you, you have to make the time of that impact longer. Just look at this. It makes it so clear. On the left, you've got a really short, sharp collision. To get the job done in that tiny amount of time, you need a massive, massive force. But look at the right. If we can just stretch out that same exact change in momentum over a longer time, the force needed just plummets. It's way, way smaller. And boom, right there, that is exactly how an airbag saves your life. An airbag doesn't magically reduce how much your momentum has to change. I mean, you still have to go from moving to a dead stop, right? But what it does, and it does it brilliantly, is it increases the time it takes for you to stop. And by stretching out that time, it cuts down the peak force that hits you, which can be the difference between walking away and, well, not. Okay, so this whole force and time thing, it leads us directly to probably the most important, the most powerful rule in this whole area of physics. It's called the law of conservation of momentum. And let me be clear, this isn't just a suggestion. It's like an unbreakable rule of the universe. So what does the law say? It's actually pretty simple. It says that if you have a closed system, basically no outside forces messing with things, the total momentum you have before a collision is the exact same amount of total momentum you have after the collision. It doesn't disappear, it just gets moved around between the objects. And this is why physicists get so giddy about this law. It's like having a crystal ball. This one rule lets us predict exactly what's going to happen when things crash into each other, or push apart, or even explode. If we know what's going on before, we can calculate precisely what's going to happen after. It's amazing. Okay, enough theory. Let's put this law to the test, right? Let's see how it actually works in the real world. Time to break down a collision. So here's our setup. This is before. We've got car A cruising along at 10 meters per second, giving it a momentum of 10,000. And then there's van B, just sitting there, so its momentum is a big fat 0. So what's the total momentum of our whole system before they hit? Easy. 10,000 plus 0 is 10,000. Burn that number into your brain. 10,000. Crunch. The collision happens. And in this case, the two vehicles stick together, which is what we call an inelastic collision. Now, because of our unbreakable law, we absolutely know, that the total momentum of that tangled wreckage has to still be 10,000. And since we know their new combined mass is 2,500 kilograms, we can just do a little math and figure out their new speed. And what do you know? It's exactly 4 meters per second. The law worked perfectly. So that crash was a perfect example of an inelastic collision. The key thing is momentum was conserved, but a bunch of kinetic energy got, lost. It turned into heat, sound, the energy it took to bend all that metal. Now, in a perfect elastic collision, think of two billiard balls hitting, both momentum and kinetic energy are conserved. That's why they bounce off so nicely. But the main takeaway? In both types, momentum is king. It's always conserved. The real difference is what happens to the energy. Okay, we've gone through the big ideas. So, to wrap this up, let's give you a little toolkit, some tips and tricks to help you really nail this stuff and avoid the common mistakes. First, some classic mistakes you want to avoid. The number one biggest mistake? Forgetting about direction. Remember, velocity is a vector, so you got to pick a positive and negative direction and stick with it. Also, make sure your units are right, always kilograms and meters per second. And please don't ever assume kinetic energy is conserved in a car crash. It's just not. And hey, if you're studying for a test or something, these tips are pure gold. Always write down the formula first before you plug in the numbers. Clearly show which way you've decided is positive. Don't forget your units in the final answer. And when things stick together, just remember to add their masses up to make one new, bigger mass. And here's one last thing, a super simple memory trick for that main formula. For P equals M times V, just think of MV. What does MV make you think of? Moving vehicle. A moving vehicle has momentum. It's a little cheesy, I know, but hey, if it helps you remember, it works. So I want to leave you with one last thing to chew on. We've established that in any crash, momentum is perfectly conserved. It's the same before and after. But we also said that kinetic energy, the energy of motion, gets lost. So where does it go? I mean, energy can't just be destroyed, right? Well, think about